Okay, so we are looking at the first momentum practice set, free response, looking at the second problem. So this one involves interesting situation. We have a block here, identical to this one here. This one's stationary at the start. This one is going to be pushed by a plunger from here to here. So presumably it will be accelerated from here to here. Then it will move at constant velocity with no friction from here to here. Then it will move with friction, so therefore it will decelerate in here. And then starting here, it will move at whatever its velocity at the end, it will continue to move until it collides here and sticks to this one. And they will, after we apply conservation of momentum or whatever, maybe it goes off after that. Well, not maybe, but it will. So, but what's interesting is they want us to graph, if we read this, they want us to graph what the center of mass does. So we're going to be a little methodical with this to make sure we get it right. So they're identical blocks. Surface is frictionless except for components C and D, where their surface is rough. Beginning at time A, the block 1 is pushed with a constant horizontal force, so that means a constant acceleration by a mechanical plunger. Upon reaching B, block loses contact with the plunger and continues moving to the right along a horizontal surface towards block 2. This will be at constant velocity. They don't tell you that, but you're supposed to know Newton's first law. If there's nothing else, no friction, no plunger, constant velocity for that. Block, this is a point E, after which the two-block system moves. Okay, so here's what we need. What I think we need to do is we have to establish what the center of mass is doing, not just what this one's doing, but what is the center of mass doing. And what you want to keep in mind is two blocks are identical. So I would suggest at each location, let's sketch up. So we'll use pink for block 1. So at the beginning, block 1 is located here. All right. And block 2 is located, we'll use like blue for that, located at E. There's 2, and there's 1. Now where would their center of mass be? Well, exactly halfway in between them. So I tried to scale this out. 1, 2. So it'll be right here at C. Center of mass will do something noticeable. We'll try green. And the center of mass will just be a dot. So initially, the center of mass is here. CM. Okay. Then what happens? Well, this thing is accelerated from here to here. So I'm going to try doing it this way. I'm going to say, all right, so the next time we see it, block 1 is here, 2 has not moved. The center of mass will be right in between them, which is now here. Now, that means the center of mass went from its old position here to its new one here. It covered whatever this distance is in whatever time it took A to move from there to there. But how did it move that? Because when you go to graph it, one of the things you have to point out is, did the center of mass move at a constant velocity? Did its velocity increase? All right. Did it slow down? Did it speed up? Did it, I guess increase would be accelerated. So we shouldn't get any, since we're doing speed in the graph, we shouldn't get any quadratics, I don't think. Because that would be a changing acceleration. And I don't think that shows up here. But the point is from here to here, it's going to follow the behavior of whatever 1 did, because 2 is stationary. Did 1 move from here, A to B, at constant velocity? Or was it applied on by a force at a plunger? And the second one. So there is an acceleration here. So that means between here and here, the center of mass also accelerates. So this time represents time A, this represents time B. They don't really care about distance. So what does this, looking at the graph, what does the speed do of the center of mass? We'll use green. Well, it starts at 0, and it picks up speed. Now, what I don't know the significance of these blocks here. I'm going to just use them to say, all right, so we'll say it picks up speed like so. The center of mass is going fast, starts at rest and speeds up. Does not say how far it goes. We can kind of picture it here, but that's not what this thing's about. But it should be an increasing line. All right. Now, so blocks, when it gets to C, block 1 gets to C, block 2 is not moved. So where's the center of mass now? It's here. Now it's moved from here to here. Interestingly enough, looks like it's moved the same distance. But how is it moved then? Well, how did 1 move from B to C? B to C, that should have moved at constant velocity. So that means the center of mass between this one and this one would have also moved at constant velocity. All right, so what does constant velocity look like here? Well, it means it doesn't change. I would say this. Now, at C to D, things get a little funky. Because from C to D, block 1 actually slows down. Now, it's still going to be going this way, because eventually it collides, so it has to. But either way, where is the center of mass? The center of mass is right here. So it ends up covering, according to this, the same distance. Although I don't know if we're seeing... I'll have to think about that. But I'm not really worried about the distance anyway. In here, I would expect it to slow down. Because there's friction and there's going to be a deceleration. So I would say deceleration, because block 1 slows down as a deceleration, the center of mass should too. So I would say that it's going to slow down. Now, is it going to slow down to a stop? Well, no, it can't, right? Because if it slowed down to a stop, then it would never hit E, and they say it hits E. So I got a couple options here. I'll bring it down to like that. If I wanted, I could redo, if I was working smart and working in pencil, maybe I could redo this graph and say, you know what, I'm going to erase that because I'm going to say it picks up speed to like here in the first segment, seems to be arbitrary, goes at constant, and drops to here. There we go. So we could use either one, doesn't matter, but there's going to be some drop in velocity. Speed's going to go down of the center of mass. And then, from D to E, so then that's when they collide. And at that instant, they're really at the same spot, we'll say. And the center of mass is also at that spot. That would have occurred at I'm going to say that would have occurred at constant velocity. I have a little bit of concern, like during, when does the collision take place kind of thing. I'm going to say this is up until they collide. This to me, this is one of the trickier parts. So, one school of thought says, it moves at constant velocity, but at some point the velocity is going to drop because they're going to stick together. So if you want to have that start to happen towards the end of this and continue into here a little bit, but somewhere in here, the velocity is going to drop. And actually, since the blocks are the same and they stick together, I'm gonna bring it in here. I'm gonna say it's here because I know that means the velocity is gonna drop to half because you doubled the mass. So I'm gonna do that. So I'm gonna say that. And I'm going to split the difference here towards the end of this and drop it in, and let's go like that. And then it should move at constant velocity less than half of what it had coming in. So if I'm doing the orange one, I would have it come in here. So if I decided to graph it this way, because this side's arbitrary, we can make it go as fast as we want, apparently. It would come in, and then somewhere around here, it would drop to halfway, which would be like in here. And would speed up that way. But that drop, I think, is going to be in a boil. There'll be points for that, recognizing that when the two blocks stick together, you have the same momentum. Since the mass doubled, the speed's going to have to get cut in half. So whatever you had, they're going to be looking to see if it's half. I don't think it matters where it is. In fact, now that I'm looking at it, why not go really high on this? It gives me plenty of room to work with. But let's take a look. Let's see, let me make sure I answered the question. On the axis below, sketch the speed of the center of mass of the two-block system as a function of time from TA to TF, the times at which the block reaches points A through F are indicated on the axis. Okay. Let's forge on and do the rest of it, and we'll come back later and look and see. I'm curious to see if I'm right, but, you know, so would you be if you were taking the test, right? But you don't get the luxury of checking. So I'll suffer through and just move on. Plunger is returned to its original position and both blocks are removed. A uniform solid sphere is placed at point A as shown. The sphere is pushed by the plunger from point A to B along with a constant horizontal force that is directed toward the sphere's center of mass. Okay. The sphere loses contact with the plunger at point B and continues moving across this horizontal surface towards point E. In which intervals, if any, does the sphere's angular momentum about its center of mass change? Interesting. Interesting. Okay, so this is a little bit of rotation. This is a little bit of rotation that we haven't covered yet, but it's a good preview of it. So, good question to ask. The important point here is the sphere is pushed by the plunger from point A to point B with a constant horizontal force, and this is important, that is directed toward the sphere's center of mass. And presumably there's still no friction whatsoever here to here to here and afterwards. Alright, so here's what that all means. Quick lesson in rotation, good advanced lesson in rotation. So hopefully you paid attention, you tuned into this question, because you're going to get a good little heads up. All right. So the importance of pushing it through the center of mass of the sphere. If you push any object in such a way that your push passes through wood is directed through, like you don't have to actually touch the center mass, but this force, for example, is pointed right through the center mass of that ball. Same thing's true, and I think it's even easier to picture with a block. Okay, so you have a block, and here's its a nice uniform block. There's its center mass, and you can picture it a lot of different ways. Let's say we're in space, floating, and doing a spacewalk. Gravity's not an issue; it's not touching anything else. If your force pushes through the center of mass, the object will not start rotating. It will just move and just accelerate. But if you push off center, the object will experience a torque and will start spinning and moving in this case. So by pushing through the center, they're not starting the ball rolling. And the other thing that would roll, that could produce a torque, a force somewhere on the edge, not through the center, would be friction. Even if you push a ball in the center, but there's a little bit of friction here, the bottom of the ball is stuck there for a second. And so the whole thing starts to fall over it, and then it rolls. But if it's truly, 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 truly frictionless, pushing it on the center, that ball's not going to spin. That ball is going to move. If this is a point on the ball, like a dot on it, it would stay pointed up there. It would just move translationally. It would not rotate if there's no friction. That's not a situation you see very often because we see friction everywhere. The closest thing I can give you is if you watch bowling, and you have to ask yourself at first, why are you watching bowling? Go bowl. And you're watching bowling. But anyway, I've watched bowling. Okay, I admit it, I've watched bowling. It used to come on all the time when I was a kid. So, now I know when they let it go, that the ball's oftentimes spinning. But have you ever noticed it'll be spinning backwards, but moving forwards? Well, the lane is so frictionless that it doesn't really change. It doesn't force the ball to roll that way. If the guy or person had pushed it through the center of mass, it would slide down the lane without spinning at all. Now, eventually, the wax, I think, towards the end of the lane gets a little less. And so you get a little bit of friction, and the ball will start spinning. In fact, if you watch bowling, the ball will spin backwards, and eventually it'll stop and start spinning forwards, and that's when it bites. So, point being, is it is possible for a round object to slide translationally and not rotate if you have a truly frictionless surface. Okay. So keeping all that in mind, in which intervals, if any, does the sphere's angular momentum about its center of mass change? Okay, so when is this thing going to change its state of rolling? Well, if it's not rolling, when's the first place you think it's going to roll? There's no friction here, it's not. No friction here. But what about right at C? As soon as it hits friction, the bottom part of that ball is going to get stuck a little bit, and the top is going to rotate around, and that's what's going to start this whole thing rotating. So I would expect the first change to occur at C. But then I think its translational speed will slow down. Why? Really an energy reason. If it has so much kinetic energy, what we call translational kinetic energy, 1/2 mv squared, if it starts spinning, it picks up angular kinetic energy. Well, that energy has to come from somewhere. Where does it come from? It detracts it from the translational. So you actually would, your regular translational velocity would go down. Some of your energy would be caught up in rolling. Now, what's interesting, so I know it's going to change there. It's going to roll. It's probably going to be consistent, though, from C to D. Once it starts rolling, the question is, if it goes back into a frictionless area, there's no reason, there's no torque to stop it from spinning. So if it was spinning when it left this frictional area, it will keep on spinning. Kind of like the example I gave you with the bowler. He rolls his ball with spin, or she with spin, and it spins, but the spin has nothing to do with its motion. It just happens to be spinning as it slides down the ring. So it's going to, I would expect it to keep it. I would expect there only to be a change here. When it first experiences, it would go from no spinning to spinning, and I think that spin rate would stay the same. That's my gut feeling on this one. And I like doing these and with the risk of being wrong, because it forces thought on all of our parts. All right, so in which intervals does the sphere's angular momentum about its center of mass? I take that to mean spinning. So I would say no, change. It's not spinning here. Yeah, about its center. Its angular momentum with respect to some other point might change as soon as it starts moving, but that's not what we're talking about. B to C, I'm good there. Here, somewhere right around C to right in here is where it's going to change. And then after that, it should be the same as it was here. So while it'll be different than it was at the beginning, it only changes here. And I've given my explanation roughly. And the explanation is push through the center of mass, doesn't start it spinning. If there's no friction, there's no torque by that, so that's not going to start it spinning. the next time it will experience a force that isn't through the center of mass will be here at C. That will start it spinning clockwise. And that spinning motion will continue for the rest of the time. When it leaves the friction, that spinning motion will still occur. Because Newton's first law applies to spinning too. Once you get something spinning, you better have something to stop it. Alright, so that'll be my answer. Let's see how many points I would have gotten. Alright, we got a plunger question. Okay. Five points. 5 points. For a straight line that begins at TA and increases between TA and TB. Alright. Mine didn't go up as high, but it went up. I would have erased one of these and gone higher, I think. But I don't think where it goes, you get a point for that. It could have been that. It could have been this. Any of those would have been alright. Straight line. Don't make it all curvy. It's not a quadratic or anything. Alright, so I got that point. For a segment that is horizontal and non-zero between B and C. So in other words, not down here, but horizontal. There. I'm doing different versions of the same thing, really. So, that's how I got in that point. Check. For a segment that decreases linearly, because the friction would create a constant acceleration, so you would decrease linear between C and D. So about that. Now this is the tricky one. So I got that one. For a segment that is horizontal, non-zero, and constant, but different value from the segment from B. So yeah, you can't. It has to be lower because you've lost, right? Some speed. So you're not gonna. It'll be constant, but it can't be the same as this, is what they're saying, and it's not. So this right here and this is not. From TD through TF with no change at TE. See, I have a change at TE. Oh, they got me. They got me. Damn it. They got me. Son of a gun. Son of a gun. I should not have lost that point. Okay. For a curve that is continuous from T with the possible exception of TE. So no breaks or anything, I guess? What do they mean by... In other words, no breaks. So I would have gotten a point, I guess, for a continuous curve. But I lost a point that I should not have lost. Okay, so here's where I lost my point. If you were paying attention, hopefully you were. This is where I lost my point. This is for the velocity of the center of mass. The force when they collide, see, the two blocks are part of the system. The force when they collide is an internal force and cannot change the velocity of the center of mass. So whatever I said it was here, there's none of this dropping business. Go straight. See, I was focusing on block 1. Block 1's velocity would drop, but the velocity of the center mass would not. Because you'll notice in our drawing over here, every time block 1 moved like 4 of these blocks, the center of mass just moved 2. So after it hits, it's still going to move 2. So, yeah, I blew it. Ugh, depressing. Hopefully you paid attention to why I got that wrong. All right, but that's one of the most key points of the entire problem, is understanding that when forces are internal. So what's the thing? So if I'm doing this problem, and this is why you do these problems, the thing that I now will lock into my head, and I won't make a mistake on in the test, is to remember that the velocity of the center of mass for a system cannot change or does not change if the forces are internal. Darn it. I gotten 4 of them. That's not bad, but to me that's the most important point, and I didn't get it. but my graph didn't look too bad. Part B. Correct answer is C to D. All right, I got that one. There's 2 points. One for a reasoning that a change in angular momentum is caused by a net external torque. Okay. So my part about pushing through the center of mass, there's no external torque there. So if I say it's pushed through the center of mass and therefore will not create a torque, will not cause spin or not create a torque, then that says that. For correctly indicating that friction, C to D, is the only force producing an external torque over the, so the only time you get that external torque is the friction here. All right? And to create a torque, you have to apply a force that is a distance away from the axis of rotation. So any force that is any distance away from the axis of rotation is going to create a torque, is going to change the spinning. But any force that's through the axis, that's pointed through the, there's no distance, there's no torque. You can only move it translationally. All right, not bad. All right, I think that one's done.